Okay, so now let's try to understand some specific unitary transformations on single qubits. Some specific transformations that we'll use all the time. And in fact, it's useful to, the way we think about these unitary transformations on single qubits is as quantum gates. So I'm sure many of you know about classical circuits where you have wires that carry bits of information, and then you have gates that transform these bits in some way. So the quantum analog of that, we think of a wire as carrying a quantum bit, and then we have a gate that performs a unitary transformation on that qubit, and the output is carried on the output wire, and that's the output qubit after the unitary transformation has been performed on it. Later in the course, we'll think about quantum circuits where we have many wires carrying many qubits, and then we'll have gates which act on one or two qubits or multiple qubits, and the qubits get transformed along the way. Okay, but for now, we are just thinking about single qubits and how they get transformed as quantum gates are applied to them. Okay, so the first gate that we'll consider, which is a particularly simple one, is a bit flip. So what the bit flip does is, it's given by this transformation x here, and now of course we'd want to check that x is a unitary transformation. So what we want to do is look at what's x dagger. But now, since x is real, of course, and it's symmetric, when you do the conjugate transpose, you'll just get back x itself. Okay. And in fact, you can even check that x squared, x times x dagger equal to x dagger times x, well, is just the identity. So it is in fact a unitary transformation. And okay, so what does x do? If you start off in the 0 state, then x times 0 is the 1 state, and if you start in 1, then you end up in the 0 state. And so it's a bit flip. But of course, the qubit might start in a superposition of 0 and 1. And so if you apply x to this superposition, then 0 and 1 swap places. So you end up in, well, the amplitude of 0 is now alpha 1, and the amplitude of 1 is alpha 0, because 0 and 1 swap positions. Here's another gate that's interesting. It's called the phase flip gate. It's given by this transformation z. And once again, z dagger is equal to z. And so z times z dagger is just z squared, which is the identity. So this is another unitary transformation. And what it does is it leaves the 0 state alone, but applies a phase of -1 to the 1 state. Now, of course, an overall phase is never, it's irrelevant. But what this means is that if we start in the superposition of 0 and 1, then the relative phases of these two get changed by the z gate. And so you end up in alpha 0, 0 minus alpha 1, 1. Okay, it's useful to think about this geometrically. So the bit flip, one way you can think about it is that it's a reflection of this picture, the 0, 1, about the 45-degree line. Okay, about this 45-degree axis. But now, if you were living in three-dimensional space, then you could also think about it as a rotation, a 180-degree or pi rotation about this 45-degree axis. because what you would do is you would rotate about this axis, and 0 would, let's say, come off the plane and 1 would go under the plane, and they'd keep rotating until they'd be in the orthogonal plane, and then they'd keep rotating until they switch places when you go all the way around. But now remember, we are working in not the two-dimensional real space, but we are working in a complex two-dimensional space. And so what happens is, in this complex two-dimensional space, you actually have enough room to do this rotation about this 45-degree axis. You have these, the imaginary directions where you can actually do this rotation. And so x is really a rotation, a pi rotation about this 45-degree axis. Similarly for the phase flip, well, the phase flip, what does it do? Well, if you were to draw 0 and 1 here, then what it does is it leaves the 0 axis alone, but it flips 1 to -1. And so it's a 180-degree, well, you could think of it either as a reflection about the 0 vector, or again in the complex plane you can think of it as it's a rotation through 180 degrees or pi about this axis, about the axis of the x-axis. Here's another way to think about the phase flip. So what does the phase flip do to the plus state? Well, remember, the plus state is 1 over square root 2 0 plus 1 over square root 2 1. And so what it does is it leaves 0 alone, but it applies a phase of -1 to 1. And that's exactly the minus state. And similarly, z, when you apply it to the minus state, gives you plus. And so what it's doing is, if you look at the plus and minus states, then it's swapping these two. And that's still this 180-degree rotation about the 0 axis. Okay, so now let's look at the third gate, which is called the Hadamard gate, or the Hadamard transform. This is one of the most basic quantum gates. And what it is it's given by this transformation in which all the entries are 1 over square root 2, except the lower right entry, which is -1 over square root 2. So once again, h dagger is equal to h. If you take the conjugate and then transform, you get back the same matrix. And you can verify that h squared is the identity. H times h dagger is the identity. So it's a unitary transformation. And now, let's see what happens if we start with the 0 state and apply this gate to it. Well, if you start with 0, you get the first column, which is 1 over square root 2 0 plus 1 over square root 2 1, which is a plus state. And if you apply h to 1, get the second column, which is 1 over square root 2 0 minus 1 over square root 2 1, which is the minus state. And similarly, h of plus is 0 and h of minus is 1. Now, if you look at this a little more closely, when you apply h to 0, well, you get an equal superposition of 0 and 1. So if you were to measure after applying h to 0, you'd see 0 and 1 with equal probability. And similarly, if you apply h to 1 and then measure, you'd see 0 and 1 with equal probability. So it seems as though the information about whether you started with 0 or 1 is lost when you apply the Hadamard transform. But actually it's not. the information is all put into this sign here, whether the phase is plus or minus. And in fact, the way we know that the information is not lost is because when we apply the Hadamard gate twice, we get back to the bit that we started from. Okay, so we saw how to think about geometrically think about the bit flip, the gate, the X gate, and the Z gate. Now let's look at the Hadamard gate and try to understand what it looks like geometrically. Well, so remember what the Hadamard gate does is it swaps between 0 and plus, and it swaps 1 and minus. And so one way you can understand it is if you take this axis which bisects 0 and plus, so this angle will now be pi by 8. Then what the Hadamard gate, you can think of it as is a reflection about this axis, the pi by 8 axis. But again, the right way to think about it in the complex two-dimensional space is as a rotation through pi by 8 through 180 degrees, or pi, about this pi by 8 axis. So it's a rotation about this axis where everything is rotating by pi. Okay, so finally, let's think about the following question. So suppose that you wanted to implement a phase flip gate. So suppose I wanted to implement the phase gate, or Z. But suppose that I happen to have no phase flip gates around, but I had a bit flip gate and a Hadamard gate. Would I be able to implement a phase flip gate? Well, here's a way of doing it. So remember what the phase flip does. So if you write it out, what Z does is, if you give it as input the plus state, then it outputs minus, and if you give it as input minus, then it outputs plus. Right? And if I can design some gate which transforms plus to minus and minus to plus, then it must be the phase gate. Okay, so how do we write out, how do we create a gate that transforms plus to minus and minus to plus, which swaps plus and minus? Well, what we can do, if we are not given Z, is we can first start by transforming plus to 0 and minus to 1. We can do that by applying a Hadamard gate. Okay, now that we've done a Hadamard gate, we can of course apply an X gate and swap 0 with 1 and 1 with 0. Right? So if we now apply an X gate, then 0 gets transformed to 1 and 1 gets transformed to 0. And now if we apply a Hadamard again, what happens? Well, if you apply a Hadamard again, we transform 1 to minus and 0 to plus. Okay, so what is this sequence doing for us? It's transforming. If we start with a plus state, then our output is a minus state, and if we start with a minus state, our output is a plus state, which is exactly what we wanted. So what we can say is that Z is equal to H X H. Okay. In fact, here's another way to picture it. Okay, so what this is, what this diagram is showing you is that what the Hadamard does is it swaps 0 and plus, it swaps 1 and minus, X swaps between 0 and 1, Z swaps between plus and minus. And so if you wanted to perform Z, where you want to swap these two, another way you can do that is you perform H, X, H. If you want to perform X, another way to achieve that is you do H, Z, H. Okay, what does this correspond to in terms of linear algebra? Well, what you're really doing is we're saying that Z the transformation Z is the same transformation as X if you do the transformation in the Hadamard basis. So this is really a basis change. What we are really saying is that if we perform the Hadamard transform, then we perform X, and now we perform the inverse of the Hadamard transform to move back to our original basis, then we get that's the Z transformation. But of course, remember that H inverse is equal to H. And so of course we can write this as Z equal to HXH.